Welcome back, guys.
Hello.
How's everyone doing? Hopefully everyone's doing okay.
Nope.
All right. Nope. Uh-oh. So all we can do is keep plugging away here. Just a quick note concerning, don't forget that I do have office hours on Mondays. Do drop by if you have any questions. If those from 1 to 2, if that time doesn't work, message me and I will make arrangements for an alternative time. So I'm always available. I do my best to answer your questions as I get them in my email. But sometimes it's best to actually explain things face to face. Okay. But so if I don't get back to you right away, bear with me. You eventually I'll get there. I got 25 here, 25 in the other one, 24 in the other one. So it takes a little time to get through all this. I do get quite a bit of questions, especially in the beginning weeks. Anyway, I want to, okay, Amanda, you're, okay, good question. But let's finish chapter 5, and maybe things will be a little bit clearer, okay? And if not, again, shoot me an email or arrange for alternative times for Zoom, okay? All right, so just a quick check. I'm gonna share with you the calendar to give you an update in case you're not following it. But we do have exam number 2 coming up, the 29th. It'll be covering chapters 4 through 5. I did spread out the homework. Obviously, it's not going to be due until after we're done with the chapter, so I can move those homework due dates as needed. Okay, but right now I think they're spread out far enough right now that you hopefully shouldn't have a problem. Okay. Let's go back to where we ended up, and we ended up here. Now, what we're dealing with here, to kind of refresh your memory a little bit, is we got the model of the nucleus where the protons and the neutrons exist. Did not know where the electrons were. We went through the example of taking these elements and exciting them, which then they emitted light, and then we run it through our analyzer, and we're able, from that information, we were able to come up with a model that tells us that these electrons are not just spread out all over the atom, but actually are in specific layers, okay? And in specific orbitals. We have 4 orbitals, the S, denoted by the letter S, P, D, and F. Okay? And what we've been doing is talking about the electron configuration to explain where the electrons are. And there is a notation here on how to show where the electrons are. Now, previous slide, let me back up a little bit. You had that particular chart that shows you how to fill these different orbitals, okay? And let me see what it says here. Okay. So you can use that chart and just follow it through, okay? But when we're done with this chapter, I'm going to give you an alternative way to do it, which is using the periodic table and the position of where the atom is, and not having to memorize this. But if now you got 2 ways to do an electron configuration, using this graph or this table, or using what I'm going to demonstrate here in a little bit. All right, so we talked about the noble gases, and the reason the noble gases are very stable, or quote happy, whatever happy may mean, really it's unreactive. They're very unreactive because the outermost shell, what is denoted as the valence shell, the valence electron, they're full. And they're actually full with this magic number that 8. That is, there's 8 valence electrons on the outermost shell for these noble gases, with the exception of helium, because helium only has 2 electrons to work with. And so it only has 2. So its happiness is what we call a duet. The drive in chemical reactions is to obtain that magic 8 number, or the octet rule, as it's called. And that is a driving force. And what happens is, and I mentioned this to put this in long-term memory, is that all metals, remember we talked about the elements that are metals, there's a whole bunch of refresh your memory of who the metals are. All metals lose electrons, okay? They have the property is they want to lose electrons, because by losing electrons, they fulfill that octet rule. On the other end of the spectrum, the nonmetals, all the nonmetals, and again, you have a periodic table that showed you who the nonmetals were, want to gain electrons. And if you look at their position in the periodic table, all these nonmetals are very close to the noble gases. And when we think, if you give it some thought, the nonmetals are pretty far away from a close noble gas. So being close to the noble gases, the nonmetals want to gain electrons, okay? And by gaining electrons, they fulfill the octet and have the electron configuration now of a noble gas. I repeat that. They have the electron configuration of the noble gas in front of it. They do not become the noble gas, remember, because to become a noble gas, they have to lose or gain a proton. We're not talking about protons, we're just simply talking about loss and gain of electrons, which I stated way back when. We can lose electrons and gain electrons all day long. You're not going to change what that element is. The same is true for neutrons. By losing or gaining neutrons, you just make another isotope of that element, okay? So we're not making a noble gas. They're going to just kind of have the electron configuration of a noble gas. We talked about the valence shell, valence electrons. That is the outermost shell of the element. That's where all the actions happen. That's where all the chemicals is happening. You think about it, when we cut into something, into an onion or an apple, we're cutting outside, the outermost shell, okay? That's where all the stuff's happening. And the core elements, or core electrons, I should say, well, they're full. And they're not going to give up those electrons very readily, because it takes a lot of energy to take away electrons from the core electrons. Okay, it's a matter of energy. Nature wants to take the easy path. If you think about where those noble gases, where the nonmetals are at on the periodic table, they're in the far right. Okay, and they have a choice. If I have 7 valence electrons, it makes sense that it'd be easier from an energy perspective to just gain 1 more electron to give us the 8 than to get rid of 7 electrons. It would take too much energy. On the other end of the spectrum, especially in groups 1 and 2, those metals, they have 1 or 2 electrons in a valence shell. And it's much easier to just lose those 1 or 2 electrons than to pick up 6 or 7 electrons, okay? It's a matter of energy. This is phosphorus, okay? And here's the electron configuration for phosphorus. Here's 1s2. Remember, the coefficient in front of the orbital is the energy level, which is related to the period on the periodic table. There are 7 horizontal, we call periods on the periodic table. I'll demonstrate that here in a little bit. Okay? There's 7 energy levels. So the coefficient represents the energy level. So in the first energy level, there's only the s orbit, and that's full, okay? Because phosphorus has a total of 15 electrons. So the very first 2 electrons of phosphorus occupy the 1s orbit. So we put a superscript 2 because the s orbit can only handle 2 electrons. Okay. Now we move to the second energy level because the first energy level only has 1 orbit, the s. So I got to add some more electrons, and the only place they can go is in the second energy level. Hence we have, and in the second energy level, we have 2 types of orbits. We have the s and the p. Again, the s can handle a maximum of 2, so we stick, of those 15, we put 2 in the 2s2 orbit. And then we move across the periodic table and we see that there's 6 electrons that go into the p orbit because the p can only can handle a maximum of 6 electrons. There are three orbits. Okay, there are 3 orbits in the p, and each one can handle 2 electrons, so it's a maximum of 6. Now we're full with 8 electrons. Okay, I still have 5 more electrons to go, and I got to put them someplace because, again, phosphorus has 15, and the only place is to move up to the next energy level, which is the 3rd energy level. And in the 3rd energy level, again, we have the s orbit and the p, and we fill them up in order of s, p, d, and f. That's the order. So we fill up the s first, okay? And if you notice the trend, we're going across the periodic table. We fill up with 2 electrons in the s, giving us 3s2, and then the final 3 electrons have to go into the p, okay, 3 of them. And so now if you count all the superscripts, you should see 15 total electrons, which is the number that phosphorus has, okay? Now the outermost shell of this kind of onion of phosphorus, and we got 3 layers, the outermost shell is in the 3rd energy level, and it has 5 electrons. So again, we use the thought of energy, and you think about it and you say, okay, is it going to be easier to get rid of those 5 or just add 3 more? Okay, so from an energy perspective, phosphorus will gain 3 electrons because it has room for 3 electrons. Those 3 electrons will go into the 3p orbit, filling that up. And so now when by picking up 3 electrons, it now has 18 electrons, okay? It still has 15 protons, but it has 18 electrons now. So by gaining 3 electrons, and also note its position on the periodic table, phosphorus is a nonmetal. And the noble gas in front of it is argon. So by picking up 3 electrons, phosphorus now has the same electron configuration of argon, the noble gas. And the magic octet number, the 8, has been fulfilled, okay? On top of that, because it picked up 3 negative charges, it now has a net charge of -3, okay? Because it started off with 15 positives, protons, 15 negative electrons, has a net charge of 0, but because it has a propensity to want to gain 3 electrons because it's a nonmetal, now it has 15 protons still, but 18 negatives. And the net is a -3. The question was, are semimetals gain electrons? Okay, well, remember the term semimetals. Because they're semimetals, they have the property of behaving like both metals and nonmetals, meaning that depending on the conditions, they will gain or lose electrons, okay? No, but they're not considered metals. That was the question brought up in chat. They're not considered metals because they're semi-metals because of the property of having like a mule having the properties of horse and the donkey. Okay. All right. Good question. Where am I? So if we look at the electron configuration, in this quick question, they're asking you to determine the valence electrons of chlorine, beryllium, and aluminum. Well, to do that, let me quickly pull up the periodic table because you don't have to memorize it. You just find it on the periodic table. I mean, you're welcome to memorize it. I'm not stopping you from memorizing by far, but use your periodic table. Okay, let's go to the one that I haven't marked up. Hope everyone can see that. The question was, how many valence electrons does chlorine have? So we're going to find chlorine. Chlorine is number 17, okay? And so let me mark it so we know where it's at. And chlorine's right there, okay? There's chlorine. Well, we go up, it's in the column, we go up to the Roman numeral. And that Roman numeral is 7. If you're not familiar with the Roman numeral notation, the letter capital I is 1. The letter capital B is 5. Okay, and X is 10. Now, if you go across the periodic table, just with the A elements, all the way in the far left, you see Roman numeral 1A. Next column in, 2A. Then we shoot across to element number 5. You see that 3A. And then you see the next one in carbon, where you see IV, which in Roman numeral numbering means it got the I in front of 5, so you subtract 1, okay, so that is group 4, okay? And then next one is V, which is group 5, and then if you put that I after the V, you add 1 to 5, so that's 6, and then double I is 7, and then triple I, the last one, is 8. Those are the groups. They also represent the number of valence electrons for those elements, only for the A elements. So going back to chlorine, we see that is in group 7, okay? It has 17 electrons, atomic number 17. Of those 17, 7 of them are the valence electrons. Look at the one in front, on top of it, chlorine. Chlorine has 9 total electrons. Of those 9, guess what? It has 7 in the valence electrons. And the same is true for bromine and iodine. They all have different total number of electrons, but they share the number of valence electrons. They all have 7 valence electrons. If we go over to beryllium, we got to find it. Beryllium's way over here in the far left. It is a metal. It is in group 2. What does that tell you? I have 2 valence electrons. It has a total of 4 electrons, and 2 of them are in the outermost shell. And that's true for magnesium, Mg, and calcium, and so on down the road. Okay? If we look across, let's find aluminum. Aluminum is number 13, okay? It is in group 3. It has 13 total electrons. Of those 13, 3 of them are valence electrons. And so it's also a metal. And so with respect to losing electrons, aluminum is going to lose 3 electrons and ending up with a positive charge to form the aluminum ion. Sodium, that's a total of 11 electrons, okay, based on its atomic number. Of those 11, 1 is in the outermost shell. It has 1 valence electron. And so does lithium. And guess what? Even though hydrogen is a non-metal, it has 1 electron in the outermost shell. And all the way down to everybody in the group. So that's why we put them in the group. That's why those electrons, with respect to the A elements, are in the same group, because what they share is the number of valence electrons. All the noble gases, starting with neon number 10 and argon and krypton, they're in group 8. They have 8, the magic 8 valence electrons, and hence are called noble gases because they're unreacting. Okay, so you can, just by finding its position on the periodic table, the element, with respect to only the A elements, okay, determine 2 things, 3 things. 1, how many protons, or you more than 4 things. How many protons, how many electrons, from rounding up the atomic number to the nearest whole number, you can calculate how many neutrons, okay, based on its position on the periodic table. You also know how many valence electrons are in that element. Furthermore, by its position in the periodic table, you can also determine whether it's a metal or a non-metal. And if it's a metal, it's going to lose electrons. If it's a non-metal, it's going to gain electrons. So all that information is right there in the periodic table, okay? Without having to memorize specific data for each particular element, okay? Just based on their position on the periodic table, okay? All right, so let's continue and let me go back to all right. And so by finding its position on the periodic table, okay, we can quickly determine for the A elements, the ones with the letter A, how many valence electrons they have. Okay, so chlorine has 7, beryllium has 2, and aluminum has 3. Also incorporated in there are the electron configuration for each one. And you can see of those 7 for chlorine, the 7 are in the 3rd energy level, 2 of the 7 are in the s orbit, and 5 of the 7 are in the p orbit. For beryllium, the outermost number of electrons is 2, and they occupy in the 2s orbit. And with respect to aluminum, the valence electrons occupy 2 in the s of the 3s and 1 in the 3p. Okay. So this is what I just went over with respect to the numbering, the group numbering, because that also represents how many valence electrons they have. And because of them being in that group, they also have very similar reactivity. Because remember, as I stated, chemical reactions are all attributed to the electrons. That's where all the actions happen. That's where all the chemistries happen. And if you have the same number of valence electrons, you're going to have very similar reactivity, okay? And also, depending on the group, you're going to have the same amount of either gaining or losing electrons, depending on where you're at, if you're in whatever particular group you're in. Okay. And just an exception here is helium, because helium is element number 2, and there's only 2 electrons in it. So again, we can use the periodic table. We got to find it. We got strontium, bromine, argon, silicon, and sulfur. Okay, and so we can strontium, boron, argon, silicon, and sulfur. And let's go back to the periodic table. Let's use that. Okay. Okay, the first one is strontium. We got to find it, and let me mark it. Who can tell me how many valence electrons does SR have?
2.
2, exactly. Okay. The next one was bromine. How many valence electrons there?
7.
7. Exactly. It's in group 7. And then argon, which is right there. How many valence electrons?
8.
8.
8, exactly. And then we got silicon, which is a semi-metal, which can behave as both a metal and non-metal depending on the conditions. But nevertheless, how many valence electrons?
4.
Exactly. And then the last one will be sulfur. Okay. How many valence electrons there?
6.
6. And then one last one. How many valence electrons for helium?
8.
2.
That would just
No,
be 1, wouldn't it?
I was
no.
gonna say 1.
Yeah, Amanda
Or two,
got it.
two.
It's 2. Yeah, because the helium only has 2 electrons. Its atomic number is 2. You got 2 protons, 2 electrons. Okay, and 2 neutrons, by the way. Okay, so its magic number is 2. It's a noble gas. Okay. All right. So just using the periodic table again, and for the A element, you can determine the valence electrons for columns 1 all the way across to column 8A. Okay. All right. So let's head back to the slide, and there we go. Strontium with 2, bromine with 7, argon with 8, silicon with 4, sulfur with 6. Not to be confused with the total number of electrons. They're asking for the valence electrons, which is the outermost shell. Okay. Now, this question here: why do atoms want to make compounds? Why do they bond? I briefly talked about it because they want to get that magic 8. Okay. They want, by some means, which is only 1 or 2 means, you lose or you gain electrons. That's it. Okay. And by doing one or the other, you're going to have the outermost shell, the valence electron, full. And it has been fulfilled. Now, the thing to remember is when you lose electrons or gain electrons, you're going to have an overall charge now, because the elements themselves have a 0 charge. They have the same number of positive protons and the same number of negative electrons. So their net is 0. But when you start gaining electrons, now their net becomes negative. Now you may gain 1, you may gain 2, you may even gain 3 electrons. Your overall charge now is the number of electrons that you gain. On the same token, in the other end of the spectrum, if you lose 1 or 2 or 3 electrons, then you become a positive charge, +1, +2, +3. And what that magnitude is depends on their position on the periodic table and how many valence electrons they have. Okay, when we lose or gain those electrons, okay, those now are no longer elements. We call them now ions, I-O-N-S, ions. Okay, so the element, the difference between an element and the ion is the loss or gain of electrons to form an ion. That is what we ingest. When we put sodium chloride in our salt, we're not putting sodium metal, we're using sodium ion. Okay, and we're not using chlorine to put in our French fries, we're using chloride, okay, because it gains an electron. Okay, so that's what that is all about. Gain ion formation by losing or gaining electrons. For example, okay, we have sodium here. Sodium in the periodic table, number 11, has 11 protons and 11 electrons. That's an atom or an element, okay? That's the electron configuration. Okay, point number 1. Sodium, by its position on the periodic table, is a metal, okay? Therefore, it will lose electrons because all metals lose electrons. Now, point number 2, looking at the valence shell, we see there's only one lonely electron sitting out there in the S energy level in the orbit. And so you ask yourself, okay, well, to verify that it's going to lose electrons, is it easier to lose 1 or to gain 7 from an energy perspective? Obviously, yes, it would be easier just to get rid of 1 than to pick up 7 electrons. And so sodium is going to lose an electron. And specifically, it's going to lose that electron in the 3rd energy level occupied in the S orbit. Okay, and that's now its new configuration. By losing that highlighted 3s1, it now becomes an ion. And now its new valence shell is the next one in, which is in the 2nd energy level. And guess how many valence electrons are in the second energy level? 8. 2 in the S, 6 in the P. It has fulfilled the octet. So sodium ion is extremely stable. In fact, sodium element is very, very reactive. If you take a chunk of sodium and put it in some water, it reacts spontaneously. It's just dying to get rid of that reaction and that electron. Very reactive. A lot of heat given off. It reacts with water, creates hydrogen gas, and it can get hot enough to cause a little explosion. Okay. By losing an electron, now it has 11 protons. Remember, we did not change the number of protons. We just changed the number of electrons. We have 11 positives and 10 negatives. Our net charge now is a +1. Therefore, we put superscript a +1 charge up there. Notice how it is in the far left there in the slide. So there is a difference between sodium element and sodium ion, and that difference is the loss of an electron. All right, so let's take a look at sulfur. Okay, so if we take a look at sulfur, sulfur is in group 6. Guess what? It has 6 valence electrons. Do the electron configuration, we get 1s2, 2s2, 2p6. We move up to the third energy level. Find its position. You'll notice that sulfur is in the third energy level, okay? And moving across the periodic table, we fill up the s orbit with 2 electrons in the third energy level, and then we jump into the p orbits, and there's 4 left, so we write it down as 3p6, 3p4, okay? Now, point 1 for sulfur. Based on its position in our periodic table, it is a nonmetal. And what I say about nonmetals, they will gain electrons. Because think about it. I got 6 valence electrons in the outermost shell. 6. So, energy perspective. Easier to get rid of 6 or just dump in 2. Easier from an energy perspective to bring in 2 to gain 2 electrons, okay? And so when it gains 2 electrons, that 3p4 of the element has room for 2 more electrons. So it will pick up 2 electrons, okay? And so it still has 6 protons, like sodium did when it became an ion, but now it has 18 electrons, okay? And the net charge, 16 positives, 18 negatives. We got a net charge of a -2. Hence, when we write the ion, we put a superscript -2. Now, you've put the negative in front of the 2 or after 2, makes no difference. It's still -2, okay? But when we talk about charges, make sure you put either the plus or the negative charge, okay? Now, somebody's writing on the screen. Okay, so now one last factor about nonmetals. All nonmetals, when they become ions, with respect to naming them, so I'm introducing you to this part because it's a little bit early, but we're going to get to this quite a bit. We change the name. When sodium element becomes an ion by losing the electron, its name remains the same. We just call it, we distinguish the two by saying the sodium element or the sodium atom. But when it becomes an ion, it becomes the sodium ion. Notice the name sodium remains the same. We just add either element or ion. With the nonmetals, there is a complete name change. Sulfur, in this example, is the element. When it becomes the ion, we change the name to sulfide. We add the suffix IDE, okay? And if we go back to the periodic table again, and we look at all the nonmetals, so if we look at nitrogen, and I'm going to mark them all out here real quick. If we look at nitrogen and fluorine, phosphorus through chloride, And then not so much the others too, but we're going to focus on these. Okay, the ones I've highlighted. And even hydrogen. Nitrogen, that's the name for it when it's an element. It's in group 5, so it will pick up 3 electrons. And guess what we changed its name to? Nitride. Okay, and so when you see it written, there's a difference if they say you're dealing with nitrogen element, or if they write it as nitride, Nitride, we're talking about the ion. Oxygen can gain 2 electrons. It's in group 6. Okay, it's a nonmetal. When it gains 2 electrons and becomes the ion, we change the name to oxide. Okay, fluorine becomes fluoride. Phosphorus becomes phosphorus becomes phosphide, and sulfur, the one we just did, its new name becomes sulfide. Chlorine becomes chloride. Bromine becomes bromide. Iodine becomes iodide. Okay? That is correct, Amanda. So the name change is only for the nonmetals. Only for the nonmetals. We take out we add the suffix IDE. So sulfur, we get rid of the UR for sulfur, and we put in IDE. And that's how you can distinguish, and when you start writing names out between the element and the ion. Okay. Yes, and that is only when they become ions. When they're elements, the name stays the same. Nothing happens to the metal name. So hence, that's why what we put on our French fries, we call it sodium chloride. We don't call it sodium chlorine. Chlorine is the element. That's a poisonous gas. Okay, but once chlorine gains an electron, it becomes chloride. So sodium chloride, we got sodium bromide, sodium iodide, sodium oxide, sodium sulfide, sodium nitride, sodium phosphide. All those guys are ions, okay? And in both cases, the nonmetal now has the electron configuration of the noble gas in front of it. So staying on the periodic table, if we look at the first box, nitrogen, oxygen, fluorine, when they gain their respective number of electrons, when fluorine gains 1 electron, it has the electron configuration of neon. Even nitrogen's in group 5. It's going to pick up 3 electrons. And now it has a total of 10 electrons, just like neon. The next energy level, phosphorus, sulfur, and chlorine, when they gain their respective electrons, they are now have the same number of electrons as the noble gas in front of it, argon. Okay? If we go to sodium, has 1 valence electron, now it has 11 electrons, right? And we just went through an example to show you how it loses that 1 electron. Now it has 10 electrons. Now it has the electron configuration of the noble gas behind it, which is neon. So sodium fluoride share the same number of electrons as neon, okay? Fluoride has 10 and sodium ion has 10, because the driving force in both cases is to fulfill that octet. So let's go back to the slide. All right, so sometimes you're asked, you're given the question here. We've been doing the electron configuration for the elements, but sometimes they throw at you the electron configuration for the ion. Now, how do we know that? Because they present to you a charge as a superscript. In this case, we have the potassium ion, which is +1, and the nitrogen ion, which is now named nitride, has a -3, and it has the magnesium ion because that's a +2. And so when we do the electron configuration for the ion, it comes out as 1s2, 2s2, 2p6, 3p2, 3p6. Now, you can do it for potassium element and then be aware that it's the ion we're talking about, so we can take out that last valence electron, and that's the electron configuration that you get. And that is the same electron configuration as argon. The nitride, by gaining 3 electrons, now has the electron configuration of neon, and magnesium now has the electron configuration of also of neon. Same electron configuration, okay? Eventually, what we're going to be doing is putting these negative ions and positive ions together. We're going to be putting magnesium nitride together or potassium nitride together to make compounds. So here we go. We started with the element. Now we talked about them losing electrons to form ions, and now we're going to start putting them together to make compounds like sodium chloride or potassium chloride. So right now, just based on this limited information we have, we can make a couple hundred different compounds very quickly. All right, so when we talk about ionic charges, again, we use the group numbering to help us out to determine what ionic charge it would have, okay? So group 1 and group 2As, group 1A and 2A, they're all metals. They're all gonna lose electrons, okay? They will lose electrons and end up with a perspective either +1 or a +2. And so let's quickly go back here. And so if we look at group 1A in the far left, they all share 1 valence electrons, and they're all going to lose that 1 valence electron. So everybody in group 1A are going to have a net +1 charge. Everybody in group 2A are going to lose 2 electrons, okay? And therefore, they're going to have a +2 charge, +2 charge. Now, with respect to 3A, boron, which is right on the stair step, remember that stair step? That kind of helps you out where the metalloids are. That depends. We don't know for sure. Depends on the conditions. And we'll talk about how we can calculate this charge down the road. But right now, we're just looking at the metal. So from below boron, aluminum and on down, they all will have a +3 charge. Now, the guys in group 4, they're the guys that are sitting there and they're like, whoa, wait a minute. I got 4 valence electrons, okay? I'm on the fence. That means that they can either gain 4 or they can lose all 4, okay? And what they do depends on the condition. So we can't really predict other than say the guys in group 4 can lose 4, have a +4 charge, or gain 4, have a -4, okay? We don't really know until we start talking about how to calculate the charges down the road. But past group 4, for the nonmetals, so on 5, you're off the fence now. Group 5, nonmetals, all of them will gain 3 electrons. Group 6, nonmetals, all of them will gain 2 electrons. Group 7, all of them will gain 1 electron, okay? And group 8, they're not going to gain anything because they're happy. Okay? They're fulfilled, they're inert. Right? So the group they're in tells us, can also tell us not only how many valence electrons they have, but also tells us what charge they would have. Okay? And we can also use it when we get to it. Being in the group can also determine and tell you how many bonds they're going to make. We'll get to that. All right, so group 7, they're going to gain electrons, like I mentioned, in 6, all the nonmetals. Group 7, -1, group 6, -2, group 5, -3. Okay, now with this long-term memory, I can't overemphasize it. Metals, all the metals are the ones to the left of the stair step. want to lose electrons. Now, hydrogen is over there, but hydrogen is pretty special. Okay, go back to the periodic table for a second. We put it in the far left. It's put there because it only has one electron. Hence, it has one valence electron, 1s1. Okay, but hydrogen is very unique. It can lose that one electron to give us a plus charge on hydrogen. But the other cool thing about hydrogen, because it's a 1s1, it's got room for one more electron. So it can actually gain one electron to have a negative one charge. Okay, but more on that when we get to acids and bases. That's why it's put on that in group 1A. But always remember, it's not a metal. It's a non-metal. Metals all want to lose electrons, become what we call ions, but they have a specific name. Okay, when you become a positive charge ion because you lost electrons, the name for those ions are called cations. Okay, so cations have a positive charge. When nonmetals, as I said, they want to gain electrons all the time. Okay, they have their own little special name. They're called anions. Now, the term ion represents both the positive and the negative, but we break it down further to distinguish the two types of ions. Cations are positive charge, anions are negative charge. Okay, and group 4, well, like I mentioned, they're on the fence. You know, because there's 4 valence electrons, they have the capability of losing 4 or gaining 4. So they can have an overall charge from a +4 all the way down to a -4 charge. And group 8, obviously, nothing's going to happen to them because the octet is fulfilled with the exception of helium. Helium is a duet because there's only 2 electrons, okay? So across the board, using for the A elements, these are the respective charges. Group 1 +1, group 2 +2, group 3 +3, group 4 depends on the conditions. You can go +4 to -4. Group 5 would have a -3 and so forth. And the last group would have no charge because those are the noble gases. Okay, so what charge would these guys have? Lithium. Okay, we have lithium, magnesium, sulfur. We done sulfur. We done bromine, but nitrogen and aluminum. Anybody want to take a guess at lithium? What charge would it have?
Positive charge?
+1, right? Because we find lithium. Lithium's in group 1, 1 valence electron plus it's a metal. It's going to lose that 1 electron. Magnesium. Anybody want to take a gander, as they say?
+2.
Exactly. Magnesium is a metal. It's in group 2. Has 2 valence electrons. So being a metal, it's going to lose them. And then we got sulfur, which we did. We did sulfur. We did bromine. What about nitrogen?
-3.
-3 and -3. That's correct. And in aluminum, group 3, what kind of charge? It's a metal. It's in group 3. What is its charge going to be once it becomes an ion?
Well, it should be positive, right?
You got it. Positive. And so,
So it'd be a +5? Or,
no.
no.
It's 3 valence electrons. What would it be?
+3.
Exactly. +3. Now, of these, the only ones that changed their name would be the sulfur becomes sulfide. Okay. The bromine becomes
Bromide.
bromide. Okay. Oh, too many. What about nitrogen?
Nitride.
Got it. Nitride. Okay. The other ones remain the same name-wise. It will be the lithium ion the magnesium ion, and the aluminum ion, okay? Now we can actually start putting things together, because if we put together the magnesium and the sulfur, first things first, notice that magnesium has a +2 charge, and the sulfide now has a -1 charge. When we put them together to make a compound, we have to put them together such that the positives cancel the negatives. So in this case, one magnesium is sufficient to cancel the sulfur, the -2 sulfur, okay? And so this guy would be called magnesium sulfide, okay? Magnesium sulfide. If we put the lithium with the sulfide, then we have to use 2 lithiums as a subscript. So it would be lithium subscript and then the sulfur, the S, and that would be called lithium sulfide. And so here already you can mix and match, mixing the negative and positive. You don't put 2 positives together. Remember, positives repel. So you won't see 2 lithium, a lithium and a magnesium. You're going to see a lithium, a cation, and an anion. So now you can put lithium and bromide, lithium sulfide, lithium and nitride, or aluminum and nitride, aluminum bromide. So you're already starting to put together compounds. Okay, so this would be magnesium sulfide. Okay, if I had to name it. Eventually, we're going to get to the point where, given the name, you work backwards to write the formula. Or given the formula, give the name. Just like algebra, go one way or the other. Okay? Somebody has their mic on. If you don't mind shutting it off, I'm picking up some reverb here. Okay, thank you. Let me get rid of that. John, we can't see you. Okay, so remember when we're talking about gaining and losing electrons, that means what happens is you have the number of electrons of the noble gas either in front of it if it's a nonmetal, or the noble gas behind it if it's a metal. That term to say that they have the same number of electrons is called isoelectronic. Iso meaning the same, electronic meaning electrons. Okay, meaning the same number of electrons. So the magnesium ion is isoelectronic with neon, okay? Because magnesium lost 2 electrons, and now it has the same number of ions as neon, so it's isoelectronic. Notice that magnesium finds its position in the periodic table, while neon is the gas behind it, okay? With respect to the phosphide, it is isoelectronic with the gas in front of it, which is argon. They both share the same number of electrons and hence the same electron configuration. Yeah. So if we take some example of calcium, the calcium ion, the oxide ion, notice the chloride and the aluminum ion. Okay, I didn't say chlorine, I said chloride because there's a superscript negative there. If we do the electron configuration for the ions, it is given as follows. And the calcium ion is isoelectronic with argon. The oxide is isoelectronic with neon. And liquid calcium, calcium ion and the chloride ion, they share being isoelectronic with argon. And the same is true with oxide and the aluminum ion. They're both isoelectronic with neon. And in all cases now, if you notice the valence shell, the new valence shell for the calcium ion is in the 3rd energy level. And it has 8 valence electrons, okay? For the oxide ion, its valence shell, it's still the 2nd energy level, but it has 8 valence electrons now. The chloride, by picking up 1 electron, now has 8 valence electrons now, the ion does. And the aluminum, by losing 3 electrons, losing those 3 electrons that existed in the third energy level, now has the new valence shell, which has 8 valence electrons. So again, the driving force is to get to that magic 8. Okay. Now, one of these tables here, it kind of, which brings me to a question. There's a problem that you're trying to look at the atomic notation of different elements. Okay. Remember, for example, here, the superscript left is the mass number. That is the mass number is equal to the number of protons and the number of neutrons, and it's a whole number. When the subscript left, that is the atomic number. That's simply how many protons it has. And when you're going through to figure out which one of these electron configurations is correct, well, look at the symbol. The symbol, you're always going to have the first letter capitalized. If both letters are lowercase, then that's not correct, okay? Or if that notation is inverted, meaning the atomic number is on top and the mass number is on the bottom, well, that's incorrect, okay? And so by process of elimination, when you look at that homework problem, and if you're looking through all the configurations, eliminate the ones that are incorrect simply because they don't present the symbol correctly, or they don't present the position of the mass number versus the atomic number, okay? And then once you go through that process of elimination, you end up with what would be the correct, which one of the 4 would be correctly written, okay? So here we're looking at selenium 78 and aluminum 27. Okay, first question to ask you, is selenium 78 the most abundant isotope? Can anybody tell me that? How could I determine that? How can I determine if Se, selenium 78, is the most abundant isotope? Okay. What tool do you have that you can use?
You can look at the periodic table.
You got it. I need to find it. Okay. I looked at the periodic table. Find it. It's number 34. Okay. Based on the periodic table, which is the most abundant isotope of Se?
79.
You got it. Exactly, 79. So that question I asked is no, selenium 78 is not the most abundant isotope, but that's the mass number. That's what you got to work with. Okay, they're giving you the mass number. What about aluminum 27? Would that be the most abundant isotope?
Yes.
Yes, it would, because I go to the periodic table, round up the atomic weight, and I get aluminum 27. Okay. All right. So number of protons, well, all we're doing is playing with the neutrons. We haven't done anything to change the protons. So selenium 78 has 34 protons, which means it has 34 electrons. And when I subtract 78 and 34, I get 44. 44 is the number of neutrons. Okay, everybody see that? Remember, the mass number is that superscript left. That is the sum of the protons and the sum of the neutrons. Or if you wanted to say the sum of the electrons and the number of neutrons, it's the same thing. Why? Because protons and electrons are the same amount with respect to the element. Okay. Now, when we go to the next column, we're still dealing with selenium 78. So we haven't changed the number of protons. The fact that it has a superscript -2 tells you we're dealing with the ion, okay? And therefore, it picked up 2 electrons. Is it consistent with where it's at in the periodic table? Yeah. Okay, pick the 2 electrons. Yeah, excuse me, it's in group 6. Check your periodic table. It will pick up 2 electrons, so now it has 36 electrons. We haven't done anything to change the neutrons because we're still dealing with selenium-78. So that number remains the same. We shoot across to aluminum, find in the periodic table, its atomic number is 13. Look, we're looking at the aluminum element and the aluminum ion. So in both cases, they have 13 protons. We've done nothing with respect to the protons. And we haven't done nothing with respect to the neutrons, because the number of neutrons that both have, the ion and the element, is 14. The only thing that has changed is that aluminum has lost those 3 valence electrons, so now it has a total of 10 electrons. So now hopefully you can see the net charge here, because we all know that we have 13 positives and 10 negatives, which results in an overall charge of a +3. Okay. Over here we have, with selenium, we have 34 positives and 36 negatives, which results in an overall charge of a -2. Okay. So that hopefully this table breaks it out for you a little better, so you can see what's going on with respect to all the subatomic particles. Excuse me. Okay. That being said, okay, we're done with chapter 5. What I want to do very quickly is go back to my periodic table and go to 1. So, you know, you may be asked to, let's do the electron configuration for, let's pick one. Let's pick, somebody pick one. Who? Let's do, you know, keep it in the 4th energy level. Potassium. We can even go into the D here. How about zinc?
Calcium.
Calcium. Okay, let's do calcium. Okay. Now, earlier I said you can use that diagram. We got to find calcium first. Calcium's right there. Okay. You can use that diagram to fill up, write out the electron configuration, or you can use the periodic table. Okay. I prefer using the periodic table. It just gives me a lot more information. So what I do, I get and you know, you have this. It's on the course website. You can print as many as you want of these. So what I do is I take the periodic table and very quickly rewrite it. Oh, let me go down. I'm a little bit challenged, technical problem here. Let me get out of that. Okay, let me rewrite it. We're going to stick with calcium. So I rewrite it and I put in my period numbers. 1 on the far left. 1, 2, 3, 4, 5, 6, 7. Okay. Unfortunately, most periodic tables have that number already in there for you, but this one doesn't. So I write those in. Okay. So what that tells me, when we get to the chapter about the periodic table, which is the next one, these energy levels are called periods. Okay. So I might as well just call them periods. So I label them 1 through 7. And then we had that other table when I said, all right, think about the ones in group 1 and group 2. Think of those as the S elements, okay? And I've highlighted them, so I marked those S elements. Then I got the D elements, which are the ones with the B elements, Roman numeral B. They're inside, there's 10 columns right there. I marked that, those are my D elements. Then to the far left, going back to group 3A, all the way to 8A, I write down P elements. So I think of those as my P elements. And then down the bottom, 2 groups that are actually coming out of the periodic table, because you notice I wrote in the period that they're in normally, but they're brought out because the periodic table will be like this wide, it'll be very wide. So they pluck those out and they squish the periodic table in to make it more readable. Okay. And so now I'm sitting here and it said I'm to write the electronic configuration of calcium. Well, I got 20, I look it up, I find it, mark it on the periodic table so I know which one I'm dealing with. And I have, it's on the 4th energy level, okay? So I know where it's at, 4th energy level. That means, and it also has 20 electrons, okay? 20 electrons. So also I realized it's in group 2. So 2 valence of those 20, 2 of them are in the outermost shell, which is gonna be in the 4th energy level. That means the energy levels 1, 2, and 3 are full, okay? I gotta fill those up. And so I start, because I know I'm in 4th energy level, the energy levels 1 through 1s, and I don't have superscript function. So starting with period 1, that hole going across from left to right, I got of those 20, 2 of them are in the 1s, okay? So that's full. So I got to go up now to the next energy level, which is the 2nd energy level, okay? And there's, in the 2nd energy level, there are 2 types of orbits, the S and the P. Remember, I fill them up as in the order S, P, D, and F. Well, I don't have any D's here. I just got the S and the P. So S gets filled up, and keeping in mind that the max I can put in the S is 2. So I got that full. So I'm already up to beryllium. That's a total of 4 electrons. So I got to shoot across the periodic table to boron, and that's where the P elements start. And I'm still in the 2nd energy level. So that's where my P starts. So I got the P, 2P, and I got 6 columns. I'm going all the way across the neon, and that's 6 columns. So I got that full. So I've taken care of 6, 7, 8, 9, 10 electrons for the calcium's 20. So I ended up with neon, so I got to go around the horn, so to speak. Now I'm in the 3rd energy level. I start again with the S orbits. And you know that I can only put maximum 2. So that fills up magnesium. I start across sodium, magnesium. Now I go keep going across the periodic table to aluminum. That's where the P's start in the 3rd energy level. 3, I'm still in the 3rd energy level, 3, and I go all the way across the argon. That's 6 columns, which is 6 electrons, okay? Now I'm at the argon number of electrons, and now I come around the horn. I'm in the 4th energy level, okay? So 4, and calcium is in group 2, and so that's the 4th, the S orbit, and I can only put 2 in there. Okay, so at this point, that's my electron configuration. Then I have 4 calcium, just using the periodic table and just starting with hydrogen, knowing that I got 1 electron of hydrogen, that's 1s1, and shooting across the helium, that fills up the other electron to 1s2, and then just going around, all the way around. Now, if I'm asked, that's calcium number 1. When I'm asked for, let's say I'm doing 21 scandium, okay? Those are the D orbitals. Now I start filling up the D orbitals. And remember, I said that the D orbitals are 1 energy level in than the period that it's in. So 21 is in the 4th period, but the D orbits begin with the 3rd energy level. And so if I was doing number 21, then that would be, oh, come on back. Space in here. It would be 3D1. That would be the electron configuration for number 21. Okay. What is zinc? Number 30. What do you think the electron configuration will be for number 30? What could I do to just, based on what I've written so far, I can just change one number and I have the electron configuration for zinc, number 30. How many columns across the D elements? Remember how many electrons I can put in the D?
Is it 10 or 8?
No, 10. 10 is correct. That's zinc. Okay? I just go across, starting with number 21 on the periodic table. That's D1. And if I go across the periodic table, it goes D1, D2, D3, D4, and I end up in number 30, which is zinc. That is D10. Once I go back to 31, I'm back to the fourth energy level, and I'm back to the P's. So that becomes 4P1. Okay. That would be with number 31. And if I went all the way across the krypton to number 36, all I had to do is change that 1 to 6. And that would be the electron configuration for krypton number 36. Okay? And then if I want to start it again with 37, then I start with 5s. I'm going around the horn, so to speak. Number 37, 5s1. Number 38. Oh, what did I do here? 5s1, there you go. Okay, that's number 37. Number 38 would be 5s2. Okay? And if I started with 39 again, I would realize that 39 is in the fifth group. I'm back to the D's. So now it is 4D1, so forth and so forth. Okay? Okay, there's a question. Let me see if I can answer it. Okay, the question is the D's. The D orbits, their orbits start with one energy level. So let me restate that to make sure we're right. I did everybody here. The D, starting with 21, that's where the D orbits begin. Okay. Now, 21 is in the fourth period, and we would intuitively think, though, okay, 4D. But based on the mathematics of these equations that came out, it turns out that the D orbits are actually one energy level in from the period that they are, okay? And so the D orbits for 21, who's in fourth period, it will be 3D. For the 39, which is in the fifth period, its D orbit will begin in the 4D, okay? Now, with respect to F, depending on the period, like F would be number 58, or say 59. That's where the F orbits begin. Their energy level is actually 2 energy levels in from the period to end. So even though number 59 is in the sixth period, the F orbit will actually be in the fourth period, okay? And that all has to do with respect to the mathematics involved in the equations. Just remember, if you hit 21, you hit the D elements, and just remember, subtract 1 from the period it's in, and that's where the D is at. And if you go back to the scale that I showed you earlier, you'll see that the D jumps in there. And I'm trying to explain why it jumps in there, okay? So for the D's, which you may find, maybe not, could be an extra credit or something. If you, for the D's, when you see the D's, take the period it's in and just subtract 1. If you ever see an F element, okay, its F orbit is just subtract 2 from the period it's in. Okay? Does that answer your question? I mean, I can bring out the mathematics for mass beyond the scope of 130. Pretty big equations, though. Interesting. So it's all about energy. Okay, put it to you that way. The d orbits happen to exist in a lower energy level than the period that they're in. One energy level than the period they're in. For the F energy level, for the F orbits, their overall energy happens to exist 2 levels in from the period that element's at. And so for the Ds, which you don't have to worry about until you hit 21, number 21 forward, the Ds just subtract 1 from the period it's in. And if you ever hit number 60 into the F elements, subtract 2. Okay? Oh, 1 minute warning. Yeah, thank you. Appreciate it. Yeah, try this, see if this helps you. You know, pick any element in there and just based on what I just told you and where it's at, see if you can figure out for yourself the electronic configuration, because theoretically, given this information, any element could be done. You probably won't see some S. You might see a D or 2 as an extra credit type of deal. But other than that, feel free to bring it in, you know, or send me an email and I can maybe write it out again, or come in and do a Zoom with me and we can go over it with a specific example. Okay? Any questions, comments, concerns? Okay, sounds good to me. You guys,
Questions?
yes, you have a question?